Dear students, very good evening to all of you. In this session, I am going to cover the applications of Coulomb's law. Means how to find the electric field intensity due to infinite line charge distribution, and how to find electric field intensity due to infinite surface charge distribution, and also how to find electric field intensity on the charge circular ring. So probably in this session I am going to cover the one application of Coulomb's, that is how to find electric field intensity due to infinite line charge distribution, and we solve one problem on the infinite line charge distribution. So the topics covered, as I told you, electric field intensity or electric field strength due to infinite line charge distribution. So this derivation is very important for examination point of view. So the applications of Coulomb's law, applications of Gauss law is very important. I can expect the good marks from these type of questions. So let us see electric field is due to infinite line charge. You are observing the line charge. We say the two ends of the line charge observing A and B. So this where the charges are distributed continuously along the length of a line, and you can also consider the length of a line is infinite. You are observing the line is extending from minus infinity to plus infinity. So here we are considering the elementary length on this the line AB. DL is the elementary length, and due to this at this elementary length we have the elementary charge dq. So because of this elementary charge dq at this point, we can find the electric field intensity at the point P as a dE. You are observing we are finding the electric field intensity at the point P as a dE due to this elementary charge dq located at the point dl. So this is located at a distance L from the origin. Let capital R is the distance between the charge, elementary charge located at the length, elementary length dl, and the point P, and small r is the distance between origin and the point P, and at the point P you are observing electric field intensity dE. This electric field intensity at the point P can be resolved into two rectangular components. One is the electric field intensity along the y-axis as dEy. Another is the electric field intensity along the z-axis as dEz, which is shown. And for this the line charge distribution, as I told you, we have the charge density called rho L. Rho L is the linear charge density, which is the ratio of charge per unit length. Same thing. So as I told you, dE is the electric field intensity which can be which is required to find at the point P due to elementary charge dq located at the length dl. So the dE can be written as a dq divided by 4 pi epsilon naught r square into unit vector ar. So why we are writing ar means electric field intensity is a vector quantity. Therefore vector form of dE is vector dE is equal to dq by 4 pi epsilon naught into r square into unit vector ar. And I told you at the point P, vector dE can be resolved into rectangular components. One is along the y-axis called dEy, another is along the z-axis called dEz. Therefore, vector dE can be written as vector dEy plus vector dEz. So vector dEy is equal to dEy into Ay, vector dEz is equal to dEz into minus Az. Means what is the dEy? dEy is the magnitude of the vector dEy, and Ay is the direction of the dEy. Means dE is along the positive y-axis, and dEz is equal to dEz into minus vector dEz is equal to dEz into minus Az. dEz is the magnitude of vector dEz, and minus Az is the direction of the electric field intensity, that is along the negative z-axis. Therefore dEy, the magnitude of the vector dEy, that is also equal to d into sin theta. So refer the figure, we can write dy is equal to d into sin theta, but d is nothing but dq by 4 pi epsilon r square into sin theta, because magnitude we are writing here. Therefore d also we can write magnitude, don't write the vector. At the end you can represent in the vector form. So dq by 4 pi epsilon r square into sin theta is the dy. That is the magnitude of the vector dy. So replace dq by rho L into dl. Why? How means rho L is the linear charge density, which is nothing but ratio of dq by dl. Therefore dq can be replaced by rho L into dl by 4 pi epsilon r square into sin theta. Now this is your total electric field intensity. So dz is cancelled. Why dz is cancelled means, by considering the elementary length, so above the point O we are getting plus dz. By if you consider the elementary length below the point means, see the same magnitude of dz is obtained, but opposite direction of dz is obtained. Therefore the dz which is cancelled at the point P with the opposite dz. Therefore dz is eliminated in this case. Therefore d can be written as dy only. Therefore dy is d sin theta. Therefore dy is equal to rho L dl by 4 pi epsilon r square and sin theta, and that electric field intensity, total electric field intensity is equal to dy into sin theta, nothing but rho L dl by 4 pi epsilon r square into sin theta. So dy is rho L dl by 4 pi epsilon r square into sin theta. What is Ey? Ey is the net electric field intensity. So total electric field intensity is Ey. Therefore total electric field dy. Then total electric field intensity or net electric field intensity is E is equal to Ey is equal to integration of dy, and is equal to nothing but is equal to integration of rho L dl by 4 pi epsilon r square into sin theta. And now we can find out what is dl and what is the r, and these things we can write down. See, refer to the figure. See, L by r is cot theta. Theta is the angle between the line joining the elementary length and the point P and the line charge. So therefore L by r is nothing but cot theta. From that we can write L is equal to r cot theta. Then differentiate on both sides. We will get dl is equal to minus r cosecant square theta. Now replace dl by minus r cosecant square theta. Next, how to evaluate small r. So we have small r by capital R is equal to cosecant theta. Then small r is obtained as capital R into cosecant theta. Now substituting r square as r cosecant theta whole square and dl as minus r cosecant square theta. So what you will get? Substituting the dl as minus r cosecant square theta and r square is r square cosecant square theta in the equation, we get Ey is equal to minus rho L by 4 pi epsilon into r integration of theta 1 and pi minus theta 2 sin theta into d theta. See, as you know that length is extending from minus infinity plus infinity. So if you convert from this length to the angle, so minus infinity means theta 1 and plus infinity is pi minus theta 2. So therefore Ey is equal to rho L by 4 epsilon r into cos theta 1 plus cos theta 2 into vector Ey. See, electric field intensity due to line charge of infinite length. So when the L is ranging from plus infinity to minus infinity at the bottom, when A is positive, plus theta 1 is equal to 0 and B is at minus infinity, theta 2 is equal to 0. Now replace theta 1 and theta 2 by 0. So we get E is equal to rho L by 4 pi epsilon r into cos 0 plus cos 0 into Ay plus sin 0 minus sin 0 Az, because this Az component is eliminated, no need to write. If you want you can write, and even if you write the substitute theta and theta 1 is theta 2 is 0, sin 0 means 0 only, but cos 0 is 1. Therefore E is equal to rho L by 4 pi epsilon r into cos 0 is 1, 1 plus 1 is equal to 2 into Ay, and simplify you will get vector E is equal to rho L by 2 pi epsilon r into Ay. So this is the final and required equation on the electric field intensity due to the line charge distribution of infinite length. So electric field intensity due to infinite line charge distribution is nothing but vector E is equal to rho L divided by 2 pi epsilon naught r into vector Ay. Now one problem on this infinite line charge distribution. So uniform line charge of infinite length with rho L is equal to 40 nanocoulombs per meter, which lies along z axis. Find electric field intensity at minus 2, 2, 8 in the here. Let us see. You are observing the line charge distribution where the charges are distributing along the length of a line which is shown in the figure. The line charge which is lying along z axis also shown, and the x, y and z axis, and locate the point P, that is minus 2, 2, 8, at which electric field intensity is determined. And the 40 nanocoulombs is line charge density. Rho L is 40 nanocoulombs. We know that for the line charge distribution we have the charge density called line charge density or linear charge density. That linear charge density is measured in coulombs per meter. Here rho L is equal to 40 nanocoulombs per meter. So you are required to find the electric field intensity at the point P of minus 2, 2, 8 due to infinite line charge distribution. So let us write the constants given in the problem. So what is that? The point P of minus 2, 2, 8 is given, and rho L is also given, 40 nanocoulombs per meter. Now find out the direction of the vector, that is R is equal to what? Minus 2 minus 1 into Ax plus 2 minus 0 into Ay, that is minus 2Ax plus 2Ay. Z component is eliminated. If it is lying along Z axis, no need to write the Az component. Az component is cancelled. The magnitude of R is root 8. Unit vector R is minus 2Ax plus 2Ay. Magnitude of R is root 8. Then the direction of unit vector is minus 2Ax plus 2Ay divided by root 8. Now we write the expression of the electric field due to infinite line charge distribution, that is vector E is equal to rho L divided by 2 pi epsilon R into Ay. Substituting rho L value as 40 nanocoulombs, and epsilon naught is 8.854 10 power minus 12, or 1 by 36 by 10 power minus 9. Anyone you can choose. And R value, nothing but R is the distance between this, so this is root 8 is the R value, and Ay is minus 2Ax plus 2Ay divided by root 8. Substituting all these things, we get electric field is due to infinite line charge distribution is minus 179.75 Ax plus 179.75 Ay volts per meter. So this is the problem on electric field is due to infinite line charge distribution. Thank you for watching this video.